Good evening. My name is Dan Riskin. I'll be your moderator this evening as we celebrate Nobel Laureate Dr. Michael Houghton. Before we begin, I would first like to respectfully acknowledge that the University of Alberta is situated on Treaty 6 territory, traditional lands of First Nations and Métis people. It is an enormous honor for me to be moderating this truly historic event. And just to give you some context for who I am, I'm a scientist, I'm a science journalist, I'm an author, and I have proud roots at the University of Alberta. I got my Bachelor of Science here in 1997. I worked for a while as a researcher, but then my focus shifted from science to science communication. And now I appear on the news and in TV documentaries explaining science to non-scientists. I'm speaking to you tonight from Toronto, but please don't hold that against me. I am from Edmonton, and I do still cheer for the Oilers, so go easy on me. As a science communicator, I've made a real point of keeping an eye open for the Nobel Prize announcements every year because often I end up reporting on the science behind them. So I remember this very well. On the morning of October 5th, 5:55 a.m. Toronto time, I absolutely lost my mind when I saw that University of Alberta researcher Dr. Michael Houghton was among the winners of this year's Nobel Prize in Physiology or Medicine. Now, I don't want to brag, but let's see, 5:55 Toronto time, that's like 3:55 Edmonton time. That's pretty early. And I remember thinking, hey, I think I know about this before just about everybody in Edmonton. In fact, I thought, I may even know about this before Dr. Houghton himself. But I was wrong, as you will soon learn as we hear from our speakers in a few moments. Now, for a science communicator, the Nobel Prizes are this unique opportunity to bring complex scientific achievements to popular audiences. I've found that non-scientists are more willing to listen. They're more willing to lean in and try a bit harder when there's a Nobel Prize in the balance. But that opportunity is lost if nobody engages those audiences. And that's why I am so pleased that the U of A is putting on this event. This is a chance for all of us, scientists and non-scientists, to take part in this moment, to cheer on Dr. Houghton and to celebrate this great success with him. Now, you may feel like you're alone in your house watching this on a screen, and that may be partly true, but you're not really alone at all. More than 3,000 people are here tonight. U of A alumni, faculty, staff, students, and community members, all watching live around the globe. And it's no wonder, this is a really big moment for the University of Alberta, for the communities touched by the university, and of course, for Dr. Houghton himself. In fact, the high-level bridge is lit up green and gold in celebration tonight. And once a bridge is involved, you know that there's something very, very special happening. Although Dr. Houghton's award was announced in October, he finally got the prize on Monday, just 2 days ago, delivered by bodyguards, I'm told. But the ceremony is not until tomorrow morning in Stockholm. He shares this year's prize with Dr. Harvey Alter and Dr. Charles Rice for the discovery of the Hepatitis C virus. So here's the story. For decades, people were getting a mysterious form of hepatitis, that's inflammation of the liver, often from blood transfusions, but it was mysterious because it didn't fit the profiles of hepatitis A or hepatitis B. So researchers called it non-A, non-B hepatitis. It's a perfect name. Finally, in 1989, after years of work, Dr. Michael Houghton, with colleagues Quy-Lim Chu and George Kuo, figured out that the culprit behind non-A, non-B hepatitis was a virus. They named it the Hepatitis C virus. And thanks to their discovery, new screening methods were developed, and soon Hep C was virtually eliminated from blood supplies. In less than a decade, infections dropped more than 80%. It is no exaggeration to say that their work has saved millions of lives. But unfortunately, there's still work to be done. It's estimated that more than 70 million people in the world still live with hepatitis C, mostly in developing countries. And although there are drugs that treat the symptoms of the virus, there is still no vaccine. And of course, vaccines are front of mind in Canada today. We'll learn more about all of this in a little bit. I want to introduce our other speakers tonight. I'm joined by 4 speakers. Of course, Dr. Michael Houghton, with whom I will speak shortly. I'm also joined by Bill Flanagan, President and Vice Chancellor of the University of Alberta. Dr. Brenda Hemmelgarn, Dean of the Faculty of Medicine and Dentistry at the University of Alberta. And Dr. Lauren Tyrell, Distinguished Alumnus and Founding Director of the Kashing Institute of Virology. So first, we're going to hear a few words from three of our speakers, and then I'm going to have a conversation with Dr. Houghton. And by the way, most of my interview questions come from you, the audience, because many of you submitted questions when you registered for this event. And our team took those very seriously. We collated them into themes, and we built a whole program of questions around the questions you had. So thank you for submitting those. It's a huge help, and I hope you get the answers you're looking for tonight. So let's get started. Our first speaker is the 14th President and Vice Chancellor of the University of Alberta, Bill Flanagan.
Thank you, Dan, and thank you, all of you, for joining us here on this very special evening. When we learned on October 5th that Dr. Michael Houghton, along with Harvey Alter and Charles Rice, had won the Nobel Prize in Medicine, we knew that this was an incredible day for these three scientists. And I want to express my heartfelt congratulations to all three of them. We also knew that it was an amazing day for the University of Alberta and for Canada. And I have to confess, my first reaction was, I thought, I do not deserve to be president on this day because I am a very new president, having joined the University of Alberta in July. And really, this is the dream of every president. My goodness, to be president when one of your colleagues wins a Nobel Prize. And I really thought I'm standing on the shoulders of others, and particularly my predecessors who did so much to bring Michael to the University of Alberta. And I'm thinking in particular of President Emeritus Samarsekera, and I hope, Indira, you're watching here tonight, because I got a phone call from Indira almost, I think, within 10 minutes of Lauren finding out about this Nobel Prize. And I really just wanted to express our appreciation to you and all that you did to make this day possible for the University of Alberta. And the Nobel, of course, marks the first time in 97 years that an academic at a Canadian university has won the Nobel Prize in Medicine. And the University of Alberta could not be more proud to be Dr. Houghton's home base. As Dan had mentioned, Dr. Houghton began investigating hepatitis C in the 1980s when we knew almost nothing about the virus. In fact, all we really knew is that there was something in people's blood that was making them sick. And it was crippling the global blood supply because blood infusions were a source of infection. Dr. Houghton and his colleagues spent 7 years unlocking the virus's genetic code. When they finally discovered hepatitis C in 1989, their work had a cascading effect. Within 3 years, new screening tests virtually eliminated hepatitis C from the global blood supply. And with 7 years, transmission rates had dropped by 80%. And today, hepatitis C can be cured in 95% of cases. However, as Dan mentioned, about 400,000 people a year still die of hepatitis C. And Dr. Houghton's team plans to make a hepatitis C vaccine to bring to human trials next year. In the meantime, he's also mobilized his lab to investigate the production of a COVID-19 vaccine. It's an inspiring story of perseverance and dedication that we might expect of a Nobel laureate. Dr. Houghton's contributions to humankind continue to be remarkable. And of course, transformational research like this also requires a space to work in, tools to work with. It requires funding to keep it all going. And it needs people who believe in the people, exploring problems and looking for answers. Dr. Houghton's story reminds me of the amazing things that are possible when a community backs a brilliant idea and gives it time and support to grow. It's an example of the outstanding work coming out of the University of Alberta and out of Canada. And on behalf of our full university community, I want to congratulate Dr. Michael Houghton on his Nobel Prize. So thank you, all of you, for joining us as we celebrate this remarkable achievement. And next, I'd like to invite Dr. Brenda Hemmelgar, Dean of the Faculty of Medicine and Dentistry, to say a few words. Thank you.
Thank you, President Flanagan. Good evening, and thank you all for joining us for this very special occasion. Even though we can't gather in person, I'm thrilled that our local academic community, alumni family, partners, and supporters around the world have come together virtually. As you know, our very own Dr. Michael Houghton has been awarded the Nobel Prize in Physiology or Medicine, which he shares proudly with Harvey Alter and Charlie Rice. Their discovery of hepatitis C has transformed the lives of millions, opening research paths that led to improved blood safety and antiviral treatments. The viral infection can now be cured in nearly all patients. Scientific discoveries like this do not happen in solitude. They come through collaboration and teamwork, from sharing with our colleagues across the hall to pooling our intellectual and financial resources across international borders. It also takes time and patience to address the world's most ravaging diseases. It takes long hours in the labs, months of analysis, sometimes years of testing and retesting. And along the way, we must always keep in mind our ultimate goal. And you'll hear Dr. Houghton say this: creating better tomorrows for patients, their loved ones, and our communities. Tonight, we're fortunate to hear from Dr. Houghton himself, as well as special guest Dr. Lauren Tyrell. Michael Houghton might not have been a part of the University of Alberta community if it weren't for Lauren Tyrell. The founding director of the Kashing Institute of Virology, Dr. Tyrell was instrumental in recruiting Dr. Houghton in 2010 here to the University of Alberta and to the Department of Medical Microbiology and Immunology. Raised on a farm just west of the city, Lauren Tyrell entered the U of A as an undergrad student in science in 1960. He'd go on to graduate with a Bachelor of Science degree, followed by a degree in medicine from the Faculty of Medicine and Dentistry. After completing a PhD in pharmacology at Queen's, he returned home to train in internal medicine and become a fellow of the Royal College of Physicians and Surgeons. Dr. Tyrell has spent the ensuing decades here at the university balancing a thriving teaching career with academic administration and a tireless focus on hepatitis research and treatment. He was the Dean in the Faculty of Medicine and Dentistry from 1994 to 2004. More recently, he shifted that focus to tackling COVID-19, working on antivirals and vaccines, and advising the federal government as part of the COVID-19 vaccine task force. Throughout his career, he's earned an impressive list of accolades, including the Alberta Order of Excellence and the Canadian Medical Hall of Fame, a Fellow of the Royal Society of Canada, and an Officer of the Order of Canada. Please join me in giving a warm welcome to distinguished University of Alberta professor and alumni award winner, Dr. Lauren Tyrell, here to share a few words about his close friend and colleague, Dr. Houghton.
Thank you, Dean Hemmelgarde, for your kind introduction. And thank you, President Flanagan and Dean Hemmelgarde, for organizing this very special event to recognize Michael Houghton's winning of the Nobel Prize in Medicine for 2020. A special thanks also to Dan Riskin for being with us tonight and moderating our event. Ladies and gentlemen, I have known Michael Houghton since he led the team at Chiron to discover the hepatitis C virus. However, I really got to know Michael Houghton after he was recruited to the Kashing Institute of Virology, the Department of Medical Microbiology, and the University of Alberta in 2010. Michael is a man of many interests and talents. He is an obsessive reader, an avid sports fan for cricket and soccer, a compassionate man with broad interests from politics to social injustices. Most of all, he's a brilliant and focused scientist, a wonderful collaborator who understands the power of multidisciplinary research, and is passionate about teamwork and recognition of his colleagues. He's an inspiring individual, both scientifically and personally. Non-A, non-B hepatitis was a huge problem in medicine, particularly in the 1980s, and it was clearly associated with blood transfusions, carrying about a 6% risk every time someone was transfused. Between 1974 and 1989, many laboratories tried to find this virus and failed. Michael's vision, passion, and 7 years of hard work led his team to discover the virus in 1989. They also developed the first blood test, which was published in the same journal at the same time. And in fact, I'm just showing you a small vial that is from that very first lot of hepatitis B detection for the virus in the blood. This was given to me by Michael and Ida, and I visited their home, his wife Ida. Canadians will know how important this is, as 30,000 Canadians were infected by blood transfusions. And this was the subject of the Cleaver inquiry and the tainted blood scandal. This discovery has saved millions of lives worldwide. Every year for the last 8 years, I have supported the nomination of Michael Houghton and his two colleagues, Lim Chu and George Koo, for the Nobel Prize in Physiology or Medicine for their discovery of hepatitis C virus. Nobel candidates can be nominated by previous Nobel laureates, predetermined institutions, and on a rotational basis by selected individuals. I want to thank Michel Chrétien, the brother of former Prime Minister John Chrétien, for his strong belief in Michael and his colleagues that they were excellent candidates, and he has sponsored the nomination. I have worked with him as we've supported this for the last 3 years. There have been many great researchers working on hepatitis C, and certainly Harvey Alter and Charlie Rice are very deserving winners with Michael. A number of scientists could have been chosen. However, in my mind, any combination had to include Michael Houghton. I believed when Michael was recruited to the Kashing and the University of Alberta, Michael would win a Nobel Prize in medicine. I had someone call me from the United Kingdom who was writing a book. The book was on people who should have won the Nobel Prize and were passed over. He began to talk to me and I said, I can't continue this conversation. And I refused to give him the information he was looking for simply because I believed it was much too early and Michael would still win a Nobel Prize. Michael was recruited to the University of Alberta based on the generosity of Mr. Kashing and the Kashing Foundation that helped establish the Institute. He was also in the first round of Canada Excellent Research Shares, a program established in 2010. And it was designed to attract outstanding scientists to help initiatives like ours in the Kashing to become competitive internationally. And Michael has certainly achieved that goal. There are many key people supporting this effort to recruit Michael, and they included Joel Weiner and Jim Edwards, who were very supportive of building the buildings and worked with me on every visit I made to government ministers or deputy ministers. David Evans, who is the chair of medical microbiology and immunology. Lauren Babiak, vice president research. And Indira Samsareka, the president of the University of Alberta. From the government, Premier Ed Stelmach and Annette Trimby, now the president of McEwen University, and Dave Hancock. And from the Kashing Foundation, Selena Chow, Julia Sao, and Frida Lal. And finally, John Chu, family physician in the Faculty of Medicine, who opened many doors and guided me in the cultural interactions that were so important in this success of the Kashing. Michael Houghton has stressed the importance of his research benefiting patients. When Michael met Mr. Lee, this resonated with Mr. Lee, who stressed his desire to see the research that we were doing in the Institute bring benefit to patients. Finally, while believing Michael and knowing that the Nobel in Michael and knowing the Nobel Prizes in Physiology and Medicine are the first Nobels awarded and always on the first Monday in October, I woke up a few minutes to 4 o'clock on October the 5th and checked my iPhone, and there was nothing there, but suddenly it appeared. Nobel Prizes for 2020 in medicine, and Michael had won with Harvey Alter and Charlie Rice. I waited a few minutes because I know the Nobel Committee would contact them, and then I called Michael. His answer to me when I called him in the middle of the night, 3 o'clock his time, was, "Is everything okay?" And I said, "It's wonderful. You've just won the Nobel Prize." I thought he would have been called and notified earlier since it was already public, but they had not reached him. And I had the joy of notifying Michael that he'd won the Nobel Prize. We shared the wonderful moment and what it meant for Michael to be finally recognized, and for the University of Alberta, and for Alberta and for Canada. As mentioned, this is the second Nobel Prize in Physiology or Medicine to come to Canada. The The first was Banting and MacLeod in 1923 for the discovery of insulin. After nearly a century, Canada has its second. Michael strongly believes in the value of research to solve difficult problems in medicine. Currently, a small piece of RNA, the coronavirus, has brought the world to its knees. Research will solve our current problems of COVID-19, and we are seeing this happen now with the new vaccines. Thank you, Michael, for all your hard work, for your passion for discovery, and for recognizing the importance of teamwork. You have transformed the Faculty of Medicine and Dentistry, you have transformed the University of Alberta, and you have transformed the world. Congratulations, Michael.
And thank you, Dr. Tyrell, for that. Thank you, Dean Brenda Hemmelgarn, as well. And thank you, Bill Flanagan, for your words. So now let's get to the main event. Dr. Michael Houghton is recognized as a global leader in virology, and even before the Nobel Prize, he had received numerous international prizes for his work, including the Lasker Clinical Medical Research Award, the Robert Koch Medal, and a gold medal from the Canadian Association for the Study of the Liver. He held a Canada Excellence Research Chair in Virology from 2010 to 2017, and currently serves as director of the Li Kashing Applied Virology Institute at the University of Alberta. And now finally, he gets to speak. Welcome, Dr. Houghton. How are you?
I'm very good, Dan. Thank you very much.
Congratulations on your Nobel Prize. I'm wondering how you're feeling about the ceremony tomorrow morning. Are you nervous about that? Are you disappointed that you don't get to go to Stockholm?
Well, we've been invited next year in person to Stockholm, so we get it twice. So it's quite nice. And
so the medal arrived, you said, a couple days ago. So tell me about that. You said that there were white gloves involved in it, and I understand it was something like what happens when the Stanley Cup arrives to a building. Tell me what happened.
Well, 3 people from the Swedish embassy in Washington, D.C. flew to San Francisco. My family lives in San Francisco in the East Bay. So they flew, brought the medal, drove to my house, arrived promptly on time at 4 o'clock. And yes, we were all wearing masks and gloves. And they set up a little table in the front of my house. And we had a little ceremony where they handed the medal over. It's a beautiful medal, as well as a certificate for the Nobel Prize. So it meant a lot to me, of course. And it was a very nice gesture by the Nobel Committee.
Yeah, it is nice. And I suppose that normally that would be what happens when you're in Stockholm at that big event.
Yes, exactly.
Okay. So I've sort of divided the questions for this evening into a bunch of themes. And the first one is about your process. I think a lot of people, when they know that you've won a Nobel Prize, they want to know how you think. They want to know what it's like to be inside your mind. And so I want to start by going back to the 1980s. The world is faced with this mysterious illness, which of course is very hard for us to imagine, right? What would that be like? And you're hunting for the cause to this illness. So is your strategy when it comes to this hepatitis illness, is your strategy to try to think about it in a way that nobody's ever thought about it and be really smart about it? Or do you just apply the scientific method and bang your head against that wall the same way as everybody else does and somehow luck into being the one who gets it across the finish line? What's the secret to success there?
Well, hepatitis B was discovered in the 1960s, and in the early 70s, hepatitis A was discovered. And for the next 15 years, approximately, people around the world tried to use the methods that were successful for discovering hepatitis A and B, and they failed. So I got involved. I started in 1982. And I think what was different about our approach was to apply modern, at the time, molecular biological approaches to the problem. Methods, immunology methods, rocket diffusion, immunodiffusion, old techniques were successful against Hep A and Hep B, but they were a failure for Hep C. So we thought if we applied molecular biology, gene cloning, recombinant DNA, and allied technologies to the problem, we might get success. So that was how we started. And we tried lots of different methods that we will discuss a bit later, probably.
Yeah, and so as a researcher, you are watching the new technologies as they emerge just as much as you're watching the literature on the disease itself.
Yes, I think that's my advice to young scientists. Actually, we have exponential growth in new technologies, and they are so important. They are so enabling. It's hard to keep up to date with them because they occur so frequently these days. But it's absolutely vital for young scientists to keep up with emerging technology. And Nobel Awards in chemistry were given to the CRISPR inventors, and that's a wonderful technique that is going to be so important to human medicine. So keep up with the technology is my advice to young scientists and old ones.
Well, and so does your approach, has it changed very much since the days when you were working on that problem, or is it still really a split between the methods and the big questions?
Well, it's changed a lot, yes. It took us 7 years to identify the virus in the 80s. If we were doing it today, it probably would take 7 weeks. And that's, yes, which is...
Is that frustrating?
But that's because we did it in the 80s before the routine use of polymerase chain reaction, which is an incredibly powerful molecular biological tool, which was also awarded a Nobel Prize, and before the advent of deep sequencing. Yeah, so it's amazing. Just an example of how technology can make a huge difference.
Does it at all make you look back and say, man, 7 years of my life, if only I'd started on this a little later, I could have gotten on to other things? Or do you feel like that hard work just had to be done and you're proud to have done it?
Well, I did think about that for a few seconds, but then I realized it was worth all the pain and the effort and the disappointment to do it when we did it, 1989, because as was discussed earlier, it quickly led to the development of blood tests and diagnostics, which stopped so much post-transfusion hepatitis C. It enabled clinicians to monitor the therapy that was then available, which was interferon alpha. And it enabled the field of hepatitis C research to really begin in a big way. And lots of virologists came into the field, lots of immunologists and so forth. So yeah, it was worth the effort and the pain doing it in the 80s, even though it was tough.
And I also wonder, just in terms of your process, where does the thinking happen? Is it something that happens when you're sitting at the lab bench and you're pipetting, or is it when you're driving to work, or is it when you're at the whiteboard with your colleagues during a lab meeting? When do the ideas come to you?
Yeah, well, it usually happens interacting with other scientists, and usually not at formal meetings. It's when you're having a cup of coffee or tea and you're talking about a baseball game or a cricket match, and you then turn around to work. And in my experience, those are the best, most fertile discussions. It's those kind of random discussions you have with your scientific colleagues and medical colleagues that make the difference. It's when 2 or 3 minds connect and stimulate each other to come up with a new avenue. And that's really what we did for 7 years. And we tried many different avenues to try and solve the problem. And thankfully, one of them worked.
Now, you talk about collaborating with other people, and your work is just so collaborative, and hearing you talk about it and looking through your papers, not only are you collaborating with people within your own lab, but you're reaching out to other labs around the world. Scientists can be competitive. They can be socially awkward. Sometimes collaborating among scientists just isn't that easy. So what is your secret to herding cats? What is your secret to working with these independent thinkers and getting them aligned on a problem together and working well with others?
Well, it gives me an opportunity to acknowledge 2 key colleagues where I worked, Dr. Quilin Chu and Dr. George Kuo. They are co-discoverers of the virus. And also we had an excellent collaborator at the Centers for Disease Control, Dr. Daniel Bradley. He was an animal model expert for hepatitis C, then known as non-A, non-B. And he gave us an incessant supply of really good materials for 7 years, as well as giving us ideas and stimulation. So, to be honest, that's one of the negative things about getting big awards, that not all the team that deserves to be honored is honored. But I certainly have a huge debt to Dr. Kuo, Dr. Chu, and Dr. Bradley. How do you keep the team going together? I think everyone in biomedicine is there because they want to do some good, and they want to help people, and they want to do some research that can facilitate better treatment and better prevention. So I think that's what keeps us all going. And I think everyone was highly motivated to work on this problem. And I think the potential good you can do is what keeps you going, even though it's difficult, and even though it took us 7 years. It's the potential of helping others, helping to prevent disease, that really keeps you going. That's why we got into this field, and I got into it after reading about Louis Pasteur's life when I was 17 at high school. So, I think once you've succeeded, then quite honestly, you do have some problems where awards are not given to large teams, they're given to small teams. But I certainly want to tell George and Kui Lim and Dan that without you, I wouldn't be speaking to you right now.
I imagine between when you were 17 and you read that book about Louis Pasteur and now, that it hasn't all been smooth sailing. And we got a lot of questions from people who wanted to know how you deal with the setbacks, with the hard days, because I think it's one of the first things you learn in grad school is you get a healthy dose of failure, you get a paper rejected or an experiment that just will not work. And you were working on something for 7 years, which sort of rolls off the tongue. But I can imagine when you're in year 6 of that, you're pretty frustrated. So how do you deal with those setbacks? What's your attitude about those?
Well, I was working in the context of a startup biotech company. And of course, that takes a lot of money, and investors put pressure on the management, and the management put pressure on me, which is a natural phenomenon. So there was the pressure of that. There was the pressure from peers at the company saying, well, Mike, what are you doing? You're spending all this money in your lab and you're not making success. But ultimately, you have to believe in the aim, which is to find a major virus causing disease all over the world. And, I think I considered those pressures to be small compared with how important it would be if we could solve the problem. So I think just the aim kept me going, and it was a little frustrating. I remember driving to work in the East Bay of San Francisco, and our company was in a town called Emeryville, which was, when I joined in '82, was quite run down. And over the years, they really started to renovate the whole town and started building hotels and tower blocks. And I remember thinking, well, this is a little depressing. They've built another tower block and we still haven't discovered this virus. I think if you've got to have an important aim, right? And if you do, that keeps you going, actually. It really does.
Oh, that's great. I want to talk now a little bit about the reason that we're all in different places, speaking to you right now instead of together, which of course is COVID-19. And the obvious question is, what do you take from the work you've done on this virus, Hep C, and how do you think that should be applied to COVID-19? But I saw someone else ask you that question. And in that interview, you turned it on its head. And you said that you're more interested in what you can take from COVID-19 and apply to Hep C. And I love that answer, but could you please explain what you meant by that?
Yes. Well, I think the technologies we have now discovered the causative agent of COVID-19 very quickly, deep sequencing methods. So within a matter of weeks, the virus was identified. And then in terms of making a vaccine, we have a lot of very strong tried and trusted methods to do that. And in particular, adjuvanted protein vaccines. So I think with the technologies available, COVID-19 is soluble. But I think what has happened is new vaccine technologies have emerged in the last few years, notably the RNA vaccine technology, as well as adeno-based technology. Those have never been used before to get a human vaccine approved. But what they've done is they've been able to move very fast, faster than our existing technologies. And we've seen tremendous speed in getting COVID vaccines now approved. And congratulations to the advisory committee in Canada for getting one of these vaccines approved for use in Canada. So yeah, I think it's very interesting. The technology used for COVID is really fast, and as far as we know now, it's very effective and very safe. And it's amazing. We can now apply that to hepatitis C vaccines and pretty much every other vaccine that we need to develop. So it's been wonderful. And I think also what COVID has done is everyone has come together, academics, private sector, public health, governments, and they've all worked together to speed up the whole process. So it's just proof of what mankind can do when we're all motivated and we all work together.
So, I mean, what is it that has given us this, I mean, knocking on wood and all that good stuff, but yeah, today Canada announced that they've approved this vaccine, and everybody is just, everyone's blown away that this took less than a year. So is there something about COVID-19 that made that a little easier, or are the technologies just really that much more advanced? I mean, is this a pace that we should expect in the future with other kinds of diseases, or was there something about COVID-19 that we lucked into that people don't realize?
Well, I think there were a few factors. One is the RNA technology and the adeno technology that I already mentioned. Another factor is before you can get approval for a human vaccine, you have to prove it's efficacious in humans. We can show efficacy in animal models, but regulators around the world need you to show efficacy in humans. And the great incidence of COVID infection actually enabled efficacy testing to be done very quickly. We also needed the private sector, people like Pfizer, for example, AstraZeneca, who are very skilled and very expertised at running large clinical trials. So all of that came together, and then governments basically de-risked the vaccine development for companies by buying vaccine upfront, as Canada did very effectively using multiple technologies. So all of those factors, I think, contributed to the success of the vaccine. And also, you know, the virus cooperated. There are some viruses like HIV and also Hep C, which are very difficult viruses to make vaccines against. And so the virus has to cooperate. Usually they do, but there are some very hard cases to make vaccines against, as I mentioned.
And speaking of vaccines, one of your great accomplishments is that you developed a vaccine for SARS, the original SARS, SARS-CoV-1. But of course, that never got rolled out because that disease got wiped out. And since it wasn't a threat, production stopped on that. How effective might that vaccine for SARS have been in the early days against SARS-CoV-2?
Well, it's a great question. And this is one of the major lessons, I think, of the COVID epidemic, that if we and other companies had actually produced the vaccine against the SARS 2003 strain and stockpiled it, we could have brought that out and used it to prevent a lot of the disease and fatalities of COVID, because there have been papers published this year showing that antibodies to the SARS 2003 strain do cross-neutralize pretty well COVID-19 virus. And so that's a big lesson we have to learn along with others. I think we have to stockpile vaccines as these viruses emerge in the community. And it's not as easy as it sounds. It's very expensive to make vaccines for human use under what's called GMP, good manufacturing processes. It's very expensive, but I think COVID has taught us we have to do that, and we're planning to do that with our COVID vaccine. I think also COVID is a wake-up call. Everyone knows around the world we are under constant threat from viral infections. And so I think together, and our governments do need to fund more infectious disease research, virology, bacteriology, immunology. I really think both basic research as well as translational. We've got to spend more money essentially looking after ourselves, because all virologists will tell you that other pandemics will occur in the future.
Yeah, it's sobering, and it's something that I remember hearing quite a bit, and it's sort of brushing away and not really taking it seriously as I might have. But I think the world has changed. I think everybody understands, gets it now, and also I think a lot of people realize this could have been a lot worse, couldn't it?
It could have been a lot worse. I think had we not taken precautions of wearing face masks, socially distancing, not congregating in restaurants and bars and so forth, it would just have been, well, I mean, it's already terrible. 1.5 million people around the world have died. But had we not taken those precautions, we would be talking tens of millions of deaths so far. And I think hopefully we'll be able to stop that very soon once these vaccines are rolled out.
Yes, here's hoping, certainly. I'm going to move on now to the topic of career advice, and you've given a little of that already, but we've got a lot of science undergrads in the audience and people farther along in their science careers perhaps, and also younger who are looking at your example and trying to learn what they can from it. And so let me just ask you, what advice would you give to undergraduate or graduate students right now who are on this scientific path, but are facing so much uncertainty with the way the world's been turned upside down right now? What would you say to them?
Well, I would say to any student, think carefully about what you want to do with your life, your professional life. Many people do that and decide to be doctors or researchers or whatever, but many students don't also. They kind of drift into careers. And there's nothing wrong with that, but I would advise them, it's better to think carefully about what you want to spend your life doing. What is your vocation? And even more important than that, find what your passion is, whether it's ballet dancing, putting up buildings, building roads, being a medic or a researcher. Find what you really, really want to do. Because if you're passionate, you will enjoy your career. Hard work is not really hard work when you enjoy it. And also with a passion, you're more likely to be successful. So I think that's my general advice to students. And to biomedical students, if you're already interested in medicine or research, then by definition, if you're a medic, then you're working to prevent disease and treat it. But if you're a researcher in biomedicine, my message to you is there are many, many diseases that are afflicting mankind today, for which we have very little information and knowledge about. And there's a whole list of diseases that we all know about: multiple sclerosis, arthrolateral sclerosis, inflammatory bowel disease, all kinds of diseases, and not to mention cancer, of course. So my message to biomedical students, researchers, is spend some of your time thinking about serious disease that we do not have cures for and preventatives for. They're harder to work on because often you don't have the tools to work on. You don't have cell culture methods, you don't have antibodies and so forth. But I think we need our young, bright minds to spend more time thinking about disease. It can't be 100% of your thesis or your postdoctoral fellowship, but otherwise you won't get papers and you won't get a career. But I really would like to see students spending at least some time thinking about how would they approach solving this major disease. It could be 20% of your time, 80% on more tractable research in the lab. But I really would advise you to spend time thinking, well, how can we approach this serious disease like multiple sclerosis? What can we do? Talk to your supervisor, talk to other scientists. And you are bright young people, and it's the best time to come up with great ideas. So please do it.
And so your advice then is to take a fifth of your time or some pre-allocated amount and just do the long shots that are likely to fail and just keep throwing Hail Marys, because if one of those comes through, it's going to take you in a whole new direction.
Well, Yeah, Hail Marys, but it's amazing, as we discussed earlier, if you discuss medical problems with your fellow scientists and with fellow doctors, medical doctors, you can often come up with some decent ideas and that are rational, and go ahead and try it. Yeah.
So this is an interesting one. If you were not a scientist, what would you be doing with your life?
Well, this is somewhat humorous, perhaps not completely humorous, but often when I watch movies of bank robberies, I often think, wow, if, not to use violence or to harm anyone physically, but to rob a bank, that would be an exciting thing to do. But on a more serious note, I have no idea what I would have done besides science. It was very clear to me. I consider myself very lucky. I knew at age 17 what I wanted to spend the rest of my life doing. And I feel just as motivated today as I did 50 years ago.
Well, what if you maybe just spend 10% of your time robbing banks and spend the rest of your time on the science? That might be a
great way to get, isn't it? Yeah, brilliant. I like it, Dan.
And if it works out, who'll be the wiser. So last night I was putting my 9-year-old to bed, and I was telling him how excited I was to be doing this. And I said, "Do you know what a Nobel Prize is?" He said, "Yeah." And I said, "Well, what is it?" He said, "It's a big prize for science or swimming or something." So he's a little disappointed that I'm not talking about swimming here, but thinking of him and thinking of the young people that perhaps are in the audience right now, or are the kids or younger siblings of some of the people in the audience. There are a lot of people who think that COVID-19 is going to inspire a whole generation of people that feel like it's their mission to follow up on this strange time and to do something about it. For school-age kids specifically, what advice would you give to them?
Well, I've read that medical school applications have gone up as a result of COVID. Many young people are highly motivated to train, to work and protect us against the next pandemic. So I think that's just wonderful altruistic thinking and mentality. I think, but you have to do what your passion is. So, figure what that is. And your passion has to be realistic. Maybe at some point in my life, I wanted to be an astronaut, but that wouldn't have worked because I'm scared of heights. So you have to temper it with reality, but don't talk yourself out of your dreams. If you think your dreams could come true, that you have, with the right training, you could follow a certain career pathway, then go for it, go for it. Be enthusiastic, be passionate, and give it all you got.
Wonderful. Even if it's swimming, that's great. Well, I'm certainly going to pass that on to my kids, but thank you for that. Let's talk a little bit about the University of Alberta. What was it that attracted you to come here in the first place?
A number of things. First of all, I knew Lauren Tyrell from the viral hepatitis field and thought he was an excellent scientist, had made some really good contributions, some huge contributions to hepatitis B as well as C. So I wanted to work with him, and I really liked him, and our friendship has just strengthened in the last 10 years. Indira, one of our past presidents, played a pivotal role in setting up the Canada Excellence in Research Chair program in Canada, obviously. And so the CIRC program was very seductive because it's huge grants of $10 million given to researchers, international researchers, to come to Canada and work for 7 or 8 years. So the CIRC was a strong incentive also. Thirdly, the virology at the University of Alberta was well known in California as being very strong and effective. So I knew that I was going into a very strong department and faculty. And fourthly, for me, wanting to contribute to disease prevention, I need to work in a medical school, or I need to be very close to a medical school. And so, lots of factors, and it's been a delight. I've been at U of A now for 10 years, and it really, it may surprise you, but it's been one of the most stimulating periods in my career because of all the different people I've interacted with. Great group of young scientists in my Circ lab and now in our institute, very talented young people that'll be our leaders in the future. It's also been wonderful to interact with so many really strong principal investigators across the campus, in our Department of Medical Microbiology and Immunology, and also across the entire campus. I work with physicists, for example, who have just been fantastic. And it's really a stimulating environment, the University of Alberta. It really is. Honestly, I've been there 10 years, but it seemed like, maybe 3 or 4. And it's gone so fast because it's been so stimulating to work there.
I think part of the reason perhaps it's gone so fast is that you've been so successful and you've been doing so much in the Kashing Institute. And 2020, you pivoted, you put some of your research efforts into COVID-19. So you're used to changing direction or working on projects for long periods of time. So I just wonder where you're taking your research now, and of course, whether that's changed now that you've got a Nobel Prize.
Yes, well, on COVID, we used what we've learned on hepatitis C to apply to COVID. So we are developing a Hep C vaccine at the U of A in world-class facilities. We are one of the very few universities in Canada and in the United States and anywhere in Europe that has tremendous research facilities. It has tremendous medical schools, and it has tremendous facilities for actually manufacturing vaccines and therapeutics that you can make and then test in patients in clinical trials. That's a very unique recipe. And so really, I congratulate all the leaders at the U of A, and Dr. Lauren Tyrell has been one of those that has got us to this point. I mean, really, what we have at U of A is really unique. Anyway, we're using those facilities, and we're using our knowledge of Hep C to make a recombinant protein vaccine to COVID. And our groups, our teams have shown that we can develop antibodies in animals that do neutralize the COVID virus. Lauren's lab has been looking at virus neutralizing antibodies, and people like John Law, Mike Logan, Amir Landi have shown that we're getting very good immune responses in vaccinated animals, including neutralizing antibodies at high titer. So I think what we are probably going to do in future is we're going to make some of that vaccine under GMP, and we're going to stockpile it, as I mentioned. I'd also like to point out that Lauren set up the Kashing Institute of Virology in 2010. Then he set up the Kashing Applied Virology Institute in 2013 and asked me to direct that. In practice, he and I direct it in terms of deciding what we work on and when and how to prioritize. But we have a very broad portfolio of projects. We have the Hep C vaccine. We're working with a brilliant researcher at the U of A, Jack Germandis, on Alzheimer's disease. We have a brilliant chemistry team run by Jim Neiman, who's, we think, on the verge of coming up with very novel antivirals against cytomegalovirus. We have brilliant computational scientists like Kamlesh Sahu and Khaled Barakat, who are using supercomputers to do drug screening in silico. And we're getting a lot of very interesting hits against immune checkpoints, against fatty liver disease targets. So we have a very broad portfolio, and we are really working hard, and our team really works hard. And we are expecting to make another major medical innovation in a few years' time, 4 or 5 years' time. You're never quite sure when it's going to happen, but we are there to stop disease, and we really are, and we're determined to do that.
You sound like a kid in a sandbox who's got all the toys they want and who's just living the dream. Yeah,
and I should thank, as Lauren did, the funding is, to take things into the clinic from the research labs is very expensive. Roughly speaking, to do it once with one drug or vaccine, it takes about $10 million to prove the concept in humans. Well, we have at least half a dozen programs that we think are worth testing in humans. So you can imagine the amount of money that you need to do it. And we've been very fortunate. We've had the funding from the Kashing Foundation. We really are so grateful to the Kashing Foundation. We've had great support from the government of Alberta. Given us a lot of funding to do our work. And I came in on the Canada Excellence Research Chair grant, which was a major grant, and Western Economic Development has contributed to us. So, we need so many organizations and so many people to succeed. And it's just been a wonderful experience to do this at the University of Alberta.
So big picture, where do you think, are we headed towards eliminating hepatitis C? Is that a realistic goal?
Yes, it is. Eliminating, perhaps I'll slightly modify that. I think we can have very effective control of Hep C. WHO estimates there are 2 to 3 million infections of Hep C around the world every year. I think we can bring that down to the tens of thousands. Which is near elimination, but elimination is tough. But I think we can get rid of most of the transmissions occurring around the world with appropriate vaccine schedules. And I think we know how to do that. I'm very optimistic about the vaccine we're manufacturing for clinical trials right now at the University of Alberta.
And for this audience that, of course, is thinking a lot about COVID-19, I know the future is very hard to predict, but do you have any insights, especially with the news today that Health Canada has approved this vaccine? Do you have any advice on what we might expect or any thoughts about what we should look for?
Well, I think the news is very good. It's very optimistic. I think vaccines will work against COVID. And I would reassure everyone in the community that it has been looked at very carefully by Health Canada, all the data, and it's safe and it will benefit you personally, everyone in the community, and it will benefit the community enormously. So vaccines are the greatest healthcare product in the world in terms of what they deliver for the cost. The vaccines prevent so much disease. I think we're going to have a number of good vaccines to use against COVID, and I urge everyone to take them as soon as they're offered to you.
Do you have any final thoughts that you want to leave this audience with? This will be the last time you get to speak before you're officially awarded this Nobel Prize. So these are special words that are going to last forever. So choose them carefully.
Well, I think we've said pretty much everything, I think, Dan, but it's just an opportunity for me, perhaps, just to say thank you to what is in Alberta, and keep going. Alberta needs alternate industries. We all know that, right? The oil and gas industry has been very important to Alberta, and it will be in the future. But I think we all appreciate that we need alternate industries. And I've seen biotechnology really enhance the economy of the UK. I've seen biotechnology really enhance the economy of the US. I've been part of it in both countries. I've seen it work, and I've seen the great benefit of it to mankind. And I've seen the great economic benefits and business benefits. And Alberta needs that. And we have a good health science sector in Alberta right now. We have some very good life science scientists. But my message to Alberta is keep investing in life sciences, in health sciences. We can make Alberta a major global player in biotechnology, and it will benefit all Albertans as well as Canadians. So I truly believe that, because I've seen it happen in the UK, and I've seen it happen in California.
Those are great thoughts to finish with. And I just want to congratulate you one more time on this tremendous achievement. Congratulations, and thank you again.
Thank you, Dan.
So if you want to know more about Dr. Houghton's current work or any of the exciting developments at the Kashing Institute, you can learn more at uab.ca/Nobel. And finally, as we said, the official Nobel Prize award ceremony will be live streamed tomorrow, 8:30 a.m. Edmonton time. You can be sure Dr. Tyrell will be awake by then. So if you're free, you're welcome to watch live at that same time. The URL will be the same, uab.ca/Nobel. Once more, I want to thank all of our speakers, Dr. Michael Houghton, Dr. Lauren Tyrell, Dean Brenda Hemmelgarn, and President Bill Flanagan. And of course, I want to thank you for attending. I'm Dan Riskin. Good night.